This is a graph of the heating curve of water. So just imagine for a moment if you take an ice cube out of the freezer that's below freezing, like maybe -10 degrees Celsius, and you're going to heat that piece of ice all the way until it completely boils away and is a gas. This is the process that you would go through. So this graph shows the course of the process over time. So someone has taken the time to monitor the temperature change of your ice cube as it was changing phases and heating up. So what happens first is we start with the solid phase. When the ice is a solid that's below the melting point of ice, it simply has to warm up to the melting point. So the first part of the graph shows where you have only solid ice. When you hit the blue line here that says solid and liquid, this is the point where the ice starts to melt, commonly known as the melting point. Now, interestingly enough, water will freeze at the melting point as well. We only refer to it as the melting point for some reason. But notice what happens to the temperature at the melting point of ice. Yeah, it stops changing. It's 0 degrees all the way across. So when that phase change is happening between the solid and the liquid, the temperature stops changing. So you're still pouring in energy into the system at the same rate, but the temperature stops changing until that phase change is complete. So then what happens is when all of the ice has melted, we have one pure state. Now we have the liquid phase. And you can see now we're entering the liquid only phase. And there's a long gradual increase here because the temperature will rise at a fixed rate based on the mass of the water present. Here we can use the specific heat of water to figure out how much energy is going into that piece of ice and when it's in the liquid phase. So the water has to warm up all the way to the next phase change, which would be the boiling point. And again, when you reach the boiling point, you're changing from liquid to gas, which is a phase change, and the temperature stops changing again. Notice that we have a nice long plateau at 100 degrees Celsius. So as that water's boiling, you've got two phases present, and once all of that water has been converted to the gas phase, or we would call steam, then we can go into the heating phase again. If you had trapped all that gas, you could then heat the gas itself, and it would heat at a continuous rate as a single phase. Now let's take a look at this same graph, but this time with some equations. So if we wanted to understand and calculate the energy required over the course of the phase, you can see that there are different equations we would use. We have a very familiar equation. Wherever there's a single phase present, either a solid, a liquid, or a gas, we can use the equation Q equals mc delta T, where Q represents the heat required to warm the substance, m is the mass of the substance, C is the specific heat of that substance, and delta T is the temperature change. We're very familiar with the Q3 region. That's where we're heating water. That is very typically used in calorimetry experiments because the specific heat of water is well known, and water has a high specific heat capacity, so you can use it for these experiments very accurately. Now, if you have a solid that you're melting, if you're at the first plateau at 0 degrees, notice the equation how it has changed. There's no delta T in that equation because the temperature is not changing at the phase change. So in order to figure out the energy required to melt an ice cube, you need the mass of the ice cube and you need a constant called the heat of fusion, which is represented with delta H fusion here in this graph. So the heat of fusion tells you the joules per gram required to melt ice. And the same is true when you reach the plateau for boiling. At this point, you need to know the mass of the water you're boiling and the heat of vaporization of the water. The heat of vaporization tells you the joules per gram required to boil the water. So again, all 5 phases of this graph relate to the mass of the substance. But depending on whether you're doing a phase change or whether you're just heating the substance, you would decide which equation to use. Let's look at an example. So here's an example that sort of summarizes what I was just talking about. If we calculate the amount of energy in joules needed to heat a 25-gram chunk of ice that is in the freezer at negative 10 degrees Celsius, that's the starting temperature, until it's completely boiled away to steam. Well, we have to do 4 different calculations because the amount of energy required is going to be the sum of the energy it takes to heat the ice from negative 10 to 0. So we're going to use Q equals mc delta T for region 1. Then we need to know the number of joules required to melt the ice cube. So we're going to use the second equation, Q2, which is mass times the heat of fusion of ice, to figure out how much energy is required to melt that ice cube. Once it's completely melted, we're going to go back to Q equals mc delta T. We're going to figure out how much energy is needed to raise that mass of ice from 0 degrees Celsius to 100 degrees Celsius. And then the final step in our calculation, we have to figure out how many joules are required to boil away the water. So we'd again use Q equals M times the heat of vaporization, delta H vaporization. So when we figure out the energy for each of those 4 steps, we can total them all up, and we can tell the number of joules required to make this transition from an ice cube at negative 10 degrees to steam.